we have the pleasure to have with us Olga, Chukhno, and Francesco Malandrino. Olga is from Mediterranea University of Reggio, Calabria, and Francesco is CNR. Topic is thermal aware approach to programmable networking XR use cases. So very interesting and very interesting from the networking point of view, but also very interesting from the use case point of view. I think that Olga and Francesco will give you an introduction to the topic before entering in more technical details. So Olga, Francesco, the floor is yours.
Thank you.
Thank you very
Let me
much.
start the slide. Okay. Good afternoon, everyone. So, and I'm Olga, and today with Francesca, we are going to delve into a thermal-aware approach to programmable networking, specifically exploring its implication within extended reality use case. And before we start, let's listen a small story tale, let's say. So, and this story tale will cover the content of our tutorial. So imagine a world where ordinary disappears. So when we put, for example, on extended reality glasses, so the city noise, something that is around us, our apartments, offices, etc. So it's all vanishes, and instead some forest, beach, something that we want filled with the sounds of digital creatures appears. So this would not be just a video. It will be a metaverse or a new digital world or something immersive. And here, extended reality will be a way to enter into it. So we will have extended reality wearables. It could be glasses, headsets, and so on. And it will be already more than just screens. So these devices will have also some sensors to track maybe every hour small movement, head movement, eye movement, and so on. And just with a simple tap on a temple, we will have a bright holographic screen. However, there is a problem here because this task requires a lot of processing power, and this is where we come to the third part of our presentation. So we cannot fully dive into this new digital world without a change in how our devices and our network work together now, because our glasses now couldn't do all the hard work alone, and neither edge servers or cloud can. So instead of separate, let's say, using of devices of an edge, we need to share the load. And in this case, there must be a cooperation between a wearable, so XR wearables, glasses, headset, and in the network in order to truly experience extended reality or the metaverse. And this will be our content for today. So we will begin with an introduction to the metaverse and extended reality technology. We will then explore the wearables. So we will discuss their limitation, potential load, or demands they face in extended reality applications. And finally, we will examine how novel orchestration mechanism can be designed to support extended reality. So let's move now to the first part of our presentation, and here we will cover extended reality and the metaverse. Actually, we all have heard talking a lot about the metaverse. So this term have captured a lot of attention recently. But what exactly is the metaverse? So let's compare different definitions. There are many more, but let's see these three presented on this slide and try to understand what is the metaverse. So Wikipedia describes it as a future internet. So when we have experiences, and these experiences are immersive and interconnected 3D spaces. Cambridge instead highlights the interactive and avatar-driven nature of these virtual spaces. And Investopedia brings in the technological underpinning, something like blockchain with the cryptocurrencies, and something that we need for real world like interaction or so-called economies. So here we can see The definition can vary. However, the core concept remains. So it's something that envisions a persistent, interconnected, immersive digital realm. So it's a space where physical and virtual realities can converge, and this space is driven by the extended reality, which allows us to immerse users into something really different. So let's discuss a bit extended reality. This is an umbrella term for AR, so augmented reality, VR, virtual reality, and MR, mixed reality. And when we use the term XR, we are usually referring to this entire continuum of immersive experiences, from fully physical to fully virtual, or from fully virtual to fully physical, and everything in between. So let's try to understand what is in between there. So here let's start with virtual reality. Virtual reality creates a fully rendered digital environment that replaces real world, such as we are fully immersed into something really different, so in digital world. When we are talking about augmented reality instead, it overlays digitally created content on the top of the real world scene, on something that we can see in our real life. And then mixed reality is something that combines AR and VR, blending real world environments and digital contact. So it allows both environments, virtual and physical, not only to coexist, but also to interact. We have also some other experiences. For example, similarly to AR, we have diminished reality, which removes elements of the real environment from the digital scene. Or also we have the full immersion here. So it's a situation when we are deeply engaged in the multi-sensory experience, and we can combine different technologies. Now on this slide and on the few next, I would like to show how XR is evolved. So here we can see that XR has entered the top 10 technology trends this year. And it's expected to transform such fields as education, training, retail, and entertainment. And this year and the next years, for all of us, it will be common to see, for example, students using virtual reality to relive some events in the school, in the university, in the workplaces. Augmented reality will be more often used to assist some workers, to provide some guides, and to assist in the work they are doing. So it will seamlessly be seamlessly integrated into our daily life. And of course, it will be integrated with a lot of different technologies. For example, artificial intelligence. It's rapidly driving evolution in XR because it allows to our glasses to identify some objects in our view. So we are talking about intelligent object recognition here. It's enabling more natural language processing for some voice commands, making interaction with virtual assistant seamless. So just imagine that we have an Alexa at home. Sometimes we are asking for some help, for some commands. And here in our glasses, we will have, let's say, Alexa, because we will ask to provide a route to reach some places. We will ask maybe something about the weather forecast and so on. And this will be incorporated in our daily life within a small glasses that we have. But also AI will play a crucial role in optimizing rendering of the complex virtual environments, ensuring smooth performance even with high fidelity graphics. So we are not finished on AI. Another step will be a spatial computing, which is also important, and it will allow us to understand and interact with physical world in every intelligent way. So instead of just overlaying digital contact, devices can accurately map environments, track user movement with also quite accuracy, and enable object to respond in real time. And this has already come to our life, for example, with the introduction of Apple Vision Pro, which has a special computing. So devices are evolving and we have more technologies on it. However, to truly deliver immersive experience like metaverse, XR, and so on, we have some significant requirements for the hardware to be met. So this includes very accurate digital duplication by scanning and 3D reconstruction. So this is crucial for creating realistic environments and digital twins on the top of it. We need to compress and send a huge volume of information to the network that we will render in real time. And this is quite a lot because the volume of information for XR is quite intense. We also will need very advanced display technologies because displays themselves must offer high resolution, wide fields of view, and all this we need in order to offer truly believable visual experience. However, integrating all of these requirements, let's say, into small glasses is quite complicated and challenging. So fitting powerful components, high resolution displays, and a lot of sensors to into comfortable lightweight frame like glasses, like our normal glasses. Yes, we are talking about AR or maybe VR headset. Is really difficult. So we need to have compact but powerful processors and long-lasting and also small batteries to enable this experience. This is quite contradictory, as you can see. And also we need to ensure efficient heat dissipation with these spaces, which is quite challenging. Also, we need to achieve real-time computer graphics, however, at affordable prices, because we need to ensure mass adoption. And we demand not only cost-effective specialized hardware, but also highly optimized rendering and machine learning AI algorithms to handle. Also, we need to rely on something more powerful, rely on powerful backend of computing, storage, and networking infrastructure. This means that we need to leverage edge or cloud computing resources to handle high volume of data that is required for immersive experience. And this will need to send and compress data, as we already talked before. Another technology that we need to improve is eye and hand tracking technologies, which are really important. However, we need also to, with complication of such system, we need to guarantee low latency and robust communication across various conditions. And finally, we need sophisticated algorithms for optimizing nearly or every aspect of extended reality. But that's not it. On the top of it, we need to ensure user mobility. And we need to ensure that user can interact freely and allow him to the user to navigate the area without any cables, without any anything that can prevent user to move freely. So we must focus on a wireless scenario, which also introduce additional set of settings, additional set of challenges. Here, when we are talking about extended reality, we need to introduce a novel metric. So we are not talking about only quality of service or only about quality of experience. Here we are talking about quality of physical experience. So it's something that merge factors from humans with the traditional requirements, with the quality of experience and quality of service. And this is really important because we need to avoid user dizziness. However, this metric, this expectation, this, let's say, physical experience that we want to achieve can cause additional load on the network. And let's see an example how an example of the load we can pose on the network, we can impose. So let's make this quick calculation. Human eyes can differentiate 200 distinct dots per degree and can shift across 150 degrees horizontally and 90 degrees vertically. And we arrive at 540 million pixels for full coverage of a static image. In addition, we perceive at 200 frames per second. So we need it for some high-speed immersion. Let's consider just 120 frames per second, which is like boundary to avoid emotion blur or dizziness. So consider 120 frames per second, and we also can perceive a constant ratio of 1 million levels of brightness, and up to 8 bytes, we need to fully encode colors for each. So making a quick calculation, we arrive at 518 gigabytes per second. And if we apply here a compression rate, we arrived at 1.7 gigabytes per second. It's quite a lot, don't you think, just for one user? However, this is all that we need for a starting position of the head. Let's try to add rotation of the head of our body. And so here we can freely move maybe 360 degrees horizontally and 270 degrees vertically. And here we arrive at 3.8 gigapixels for full coverage. And at 120 frames per second, this is translated into 3.7 terabytes per second. So we are already talking about the terabytes, and we are not even adjusting the focal depth to bring object in and out. So just imagine the amount of data we need to transfer, we need to handle. And all of this must be processed and delivered in real time. So within from 5 to 30 milliseconds, let's say. How it's achievable? I think that it's achievable at a couple of percent. So if you go from 0 to 100%, it's like 5-10% at max. But we are not yet close to the full satisfaction. And this is this part brings us to the second part of our presentation, and we are going to talk about extended reality wearables. Let's begin with the history. So that's a small overview of the history. It all started with some simple glasses, rudimentary spectacles in the 13th century. And then we moved to other devices and to some modern not modern at that time, head-mounted computers. And then we saw the interest and AR, VR more and more with the technology arriving. So technology became better, and we saw more products. We saw some progress, for example, with applications like Pokemon Go, with the introduction of Google Glasses, Microsoft HoloLens, and so on. And recent years, we got a lot of novel devices. And in the future, we also see promising events to come. So we see that better XR devices or better headsets arrive, smarter devices appears on the network. We are talking about generative AI to make creating 3D contact easily. And we are talking about spatial and spatial audio. We are talking about touch feedback, some realistic avatars. We are talking about location-based augmented reality application to provide experience based on where we are, and some AI assistants that will come and assist our experience in our daily life. However, to understand better what we have in what situation we have on the market, let's have just a brief overview of the modern devices, and let's compare them. So compare augmented reality devices with mixed reality and virtual devices to see the differences in the experiences. So we start with AR, and these devices overlay digital information onto our real world view. They are generally, as you may see, the most compact option. So if we compare them with VR and MR, and their functionality is usually something related to contextual information, object recognition. So we overlay our contact and some basic digital overlays. And these devices are ideal anytime when we need digital data to be integrated in our physical, let's say, workflow without any distraction. Next, you see the difference. So we had these small devices, and now we come to mixed reality. mixed reality is something that blends our digital object with the real world. So we allow interaction and also occlusion. And there are typically standalone headsets. They're larger and less compact than augmented reality glasses, but they're more compact than full virtual reality units. And such devices are good for designing, some advanced training, collaboration. So in the scenarios where virtual contact need to interact within a physical space. And finally, we came to virtual reality. So it's something that immerses the user in a different, so digital environment, and they're larger, they're most enclosed, and they're designed to totally block out all external light for full immersion. So here we have more functions, but we use them where a total presence in a digital space is important for us. And here, just have briefly step back in time and see the early VR experience. And this slide allows us to understand the evolution, to understand the efforts that were laid in this field, and that we are moving in the right direction, and that we can see that our devices now became truly more accessible, more compact, more lightweight, more comfortable to use. So to confirm that, and that the evolution of extended reality is restless, on this slide, I want to highlight that the market continues to expand the solutions, and that our devices now have significant improvements also in capabilities, and they are becoming more immersive, more comfortable, more powerful. And this is good, but it's not the end. We need to make it even better. And beyond all of this that we were talking about, it's also important to design wearables that face issues associated with size and the temperature. So because the devices must be worn, we need these devices to be small and lightweight. So this leaves very little room for bulky fans or active cooling, which is really important when we are going to deal with something very, let's say, intense, like the task in extended reality. However, also fans will bring some additional noise and the weight, so we need to avoid it. However, if we are avoiding it, we need to somehow cope with overheating, which is quite an issue in extended reality. And when some powerful processors, which we are needed for extended reality, are cramped into small unventilated spaces, they generate heat. But heat generation not only affects the longevity of the device, but it's also very critical for user safety. So there are risks of some low temperature burns if device is used during the prolonged period of time and has a contact with the skin at an elevated temperature. You can see the image on this slide, which you see the effect of the prolonged usage and the burns on the face. So we cannot afford it. We need somehow to cope with it. We need to handle this situation. But so we are going to say that maybe we can reduce the load, but we are talking about XR. So beyond the physical challenges of the size, the temperature, XR faces significant challenges in terms of computation load, because they have to deal with a significant computation load. So we are not talking not only about rendering graphics. It involves a lot of complex tasks, and many of them we need to process in real time. So it's including understanding the user movements and the environment, building or tracking the position, or also performing tasks such as object recognition and so on. So what we have is that devices are small and compact, and to face the challenges and limited on device with also limited on device capabilities, we need to offload everything that we have, or some demanding task or partially. But offloading can also have some issues. So we can use different radio technologies. We can use millimeter wave, terahertz. So when we are talking about extended reality, we are talking about high frequency communication, but also microwave can handle some tasks depending also on the application. But different radio technologies have different speeds, reliabilities, cost, and can sometimes get blocked or overloaded. So in this context, we need to understand how to best exploit wearables and their capabilities, which are growing for local processing, but we need to account for thermal management on such variables. So to do so, what we did, we studied how heat affects a wearable device. We tried to do it in real world setting and use solid multiphysics. And on this figure, you see how power use changes with the chip's temperature. So as you expect that temperature goes up when the chip works. So when we are locally process some context, some tasks, for example, machine learning inference, and goes down when the tasks are offloaded. And here you also see the purple line, which is important, which shows the safety limit in order to avoid low temperature burns. So as we saw on the figure before that people can get hurt while using something during the prolonged period of time. And also we see that if the chip works too often in a row, so the temperature can go over this limit. And this is something really important, and this is something we need to handle, and how to do it, I guess that Francesco will narrate. So I give the floor to Francesco.
Thank you very much, Olga, and thanks to all the people bearing with us. So what we are going to do now is to narrow the scope of our attention to one particular problem out of the many that Olga outlined, and specifically the problem of orchestration. If you belong to Restart, and especially if you belong to the super project, you have done a lot of orchestration. For everybody else, let's say that broadly speaking, orchestration is the task of locating within the network the resources, including networking resources like bandwidth, but also computational resources, GPUs, memory, everything that we need to perform a certain task or to provide a certain service. And in the specific case of XR, it means two things. First, deciding, like in this example coming from an Ericsson white paper, deciding how much work we are performing locally at the device and how much work we are instead offloading to the edge. Like Olga was mentioning, XR devices are capable, but at the same time they are limited in their thermal performance, in their battery. So on the one hand, we would like to do as much as possible locally, but at the same time, we don't want to cook our user. At the same time, offloading is not without its own drawbacks. First of all, it costs. And if you are the manager of an XR service, you want to keep your costs as low as possible. And also, some of the technologies, especially the higher frequency ones, which we may use for offloading, are prone to blockages or to other types of problems. So essentially, we face failure either way. So if we try to serve content locally, we may have to drop a certain request because of the wearable is overheating. If we try to offload to the edge, we may have a packet loss, so the request gets lost. And either way, we have to pay a cost. So what offloading means in this context is finding the right offloading fraction, this gamma parameter here, that minimizes the cost subject to a target probability of successfully completing the request in one way or the other. So like we mentioned, our objective is to minimize the cost. Our variable is the offloading fraction. So intuitively, what type of decision do you want to do? So if you have a case like the green user on the left, your battery is full, your wearable is cool. You see the little snowflake, which today is especially desirable. So in that case, you are more likely to perform your computation locally and to get away with that. On the other hand, if you are like the user on the right, so you have a low battery, or your wearable is high, or your wearable, your system is doing other things, so there is simply no power available to perform a certain operation, then you are more likely to offload that to the edge, and if you must pay, so be it. What can you do? So this is a very high level, the problem that we are going to look at in the next few slides. I would like also to mention that we have a submission currently under revision for networking letters, and this is the archive link describing in some more detail and some more formulas the mechanic of the problem that we face and the solution strategy. So if you are curious, of course, we are available for questions, and if you are very curious, then you are welcome to check out the archive submission. But in the meantime, let's go back to our problem. Of course, we have constraints, and constraints, broadly speaking, means we want not to exceed the capabilities of the wearable, which, as we have seen, are large but not infinite. So we have to stay within the maximum power that the wearable has, which means obeying the thermal design power, but more intuitively means do not try to do more than the wearable can do. We do not want to have the wearable becoming too hot, because then the user will get that burn that we were seeing earlier. And we do not want to deplete the battery sooner than we have to. And the thing about these three constraints, the interesting thing that these constraints operate, they work at very different time scales. The power is an instantaneous quantity. I do not want to exceed the power now. Then the temperature varies on a longer time scale, like we are seeing here, is hundreds of seconds, let's say minutes. The battery, on the other hand, is long term. So whatever decision scheme that we come up with must account properly for all the constraints, which means it must account properly for all the time scales. If we fail to do that, and we will see, we do not only have potentially solutions that we do not like, suboptimal solutions, we are probably going to get infeasible solutions. So we want to be very careful about that. And another thing, why wearable? Of course, all mobile devices have a battery, all have a limited power. Wearable are special in the sense that it is especially like the temperature is of the three constraints that we were mentioning. It is especially like that temperature is the one that drives the behavior of the wearable. Let's put it in a different way. If I have a smartphone, I am most likely to hit the power limit. That smartphone has a certain number of CPU cores, cannot do more than that. If I have something like a laptop, then the battery is more of a concern, because that thing must last for the whole day, and the operating system will stop me if I try to do too much. So the effect is temperature in the traditional wearables is less likely to be a major concern, which also means that the traditional orchestration paradigms are less likely to properly take temperature into account. Now, because we are having wearables, we are very concerned about temperature, and our decision-making schemes must account for this. So in order to compute, to check all our constraints, we go through the most important quantity of our system model, which is the power. Now, as I said, the nitty-gritty details are in the paper, but the intuition is the power that I have to consume at a certain device at a certain time is given by the product between the power requirements of the requests that I may serve locally, multiplied by my decision variable L of R, so whether I should serve locally a given request R. Then I sum them all, and this is my power over the time. Now, temperature. So we were showing a couple of slides ago this curve. Now, where do these curves come from? We know from the literature, thankfully somebody else did the hard work for us, we know that wearables can be modeled as LTI systems, so linear time invariant systems. This means that they have a transfer function. So if you remember your electronics class, the way transfer function works is that the transfer function is defined as the response of the impulse, and the consequence is that I can compute the temperature over time for a given device D by computing the convolution between this transfer function and the power, where the power, as we have just seen, is driven by my decisions. So my decisions, offloading decisions, drive the power, and the power drives the temperature through this type of convolution operation. Of course, then for the battery, you do a similar thing, but you compute the integral of the power over time, but that is less, let's say, unique to wearables, so we will not go into that. So given this system model, we also proposed a solution concept, which we call TAO, for temperature-aware offloading. And the high-level goal is what we have mentioned earlier. We make offloading decisions, we minimize the total cost, we guarantee feasibility considering all constraints, all time scales, and as we will see soon, we also want to be able to work in a stochastic setting where we do not know a lot of information on the individual request, but only some aggregated statistics. Indeed. So earlier we presented for simplicity the system model in the case where we know for every request the arrival time and the duration. Of course, this is not realistic. So what we do know is the arrival rate. So the rate at which new requests arrive at a given device. And this means that we cannot have as a decision variable, what should I do on every individual request, but only an offloading probability, which can be specific for a device. So this is what is called a randomized approach. Additionally, our approach is stationary because our decision variable, in particular the offload probability, is not changing over time. So we find the optimal, as we will see, offloading probability for every device, and that's it. And then, given this setting, we are able to rewrite our objective and our constraints in terms of CDF, so probability distributions, including parameters like the arrival rates and decisions like our offloading probabilities. Additionally, because we are in a stochastic setting, it doesn't mean much anymore to say things like, I want to guarantee the battery level. No, you cannot give an absolute guarantee. So in any stochastic setting, what you do is you set a target confidence level omega between 0 and 1, and then what you guarantee is that the probability of violating a certain constraint is lower than omega. And you enforce this by considering the cumulative distribution function, so the integral of this type of objects, and imposing that this is lower than your omega. Of course, this is good because it means that omega becomes a parameter. So you can decide in this setting, I can tolerate failure, so my omega is 0.95. Now I am fine with failing 5% of the time, and that will probably be cheaper. If you are in a factory setting, then you are not fine with failing 5% of the time. Your omega will be much higher, no, 0.099, sorry, 999, and so on. You can find decisions that guarantee you that omega, be aware that the cost is going to be higher. So this is a classical trade-off. It's not unique to wearables, but it is important that our TAO solution strategy allows you to enforce also this type of trade-off. And lastly, the equations are only there to scare you, but don't be alarmed. The thing that it is important to keep into consideration is that all the operations that we have seen, now we mentioned convolution, we mentioned integration, they are linear. This means that the overall problem that we have set, so finding the optimal offloading probability subject to the probability, the confidence level guarantee, all of this is a convex problem, and that can be solved numerically very quickly in real time. We all know Boyd's book. And why numerically? Because normally I do not know a closed form expression for the transfer function. So I will somehow measure that, characterize that, and then perform all operations numerically. If I do know everything in closed form, I can also get a closed form expression for the optimal offloading probability. And this means that in that case, I can have essentially instantaneous decisions. So for our performance evaluation, we consider two of the wearables that we were discussing earlier. They belong to different generations, and you can see also here from the very different thermal design power, duration of the local processing. And for both wearables, we consider 10 requests arriving in a 60-minute time window. And we consider as a benchmark the traditional approach of not accounting for the temperature, but only guaranteeing power and battery, which is indeed what happens in many state-of-the-art works. As we can see, this is a graph similar to the ones that we were seeing earlier with Olga. So we are the blue line, and the gray line is the state of the art, and these little arrows are the incoming requests. So if we decide to serve a request locally, the temperature goes up, and then it more or less slowly goes down. And if we do not account for temperature, as the state of the art does, you are liable to serving multiple requests close to each other in time locally, which means that your temperature goes above the threshold. So ignoring the temperature, that's not very surprising, means that you are likely to violate the temperature constraint. That's not surprising. The surprising part is, in a wearable, you are likely to violate the temperature constraint, even if you are keeping the others. So the state of the art is not some type of kamikaze approach, no, always serve locally. It is keeping the battery, it is keeping the power. Nonetheless, it violates the temperature. So you cannot assume temperature to somehow follow from the other constraints. This is the takeaway message. And yeah, this is a different view of the same phenomenon, which confirms that indeed tau is always below the threshold. State of the art violates it about 5% of the time. It doesn't sound a lot, but if you remember the bars of the slide, then you will realize that 5% is, case in point, a lot. Last, we can look at the cost. keeping care and keeping track and caring for the temperature may mean that we perform more offloading. And as we mentioned, offloading means a higher cost. However, it is important to notice here that it is not necessarily the case. So in the case of the Google Glass, so the dashed dotted lines, indeed, tau has higher costs than the state of the art. In the case of the HoloLens, it is not the case. So the two approaches yield the same cost. So it's not like tau offloads more, it just chooses differently the requests to offload, which gives us a dual view of what we have just said earlier. So accounting for the temperature is important because it allows you to properly choose not only how many, but which request to serve locally. And in many cases, you get feasible decisions, avoid cooking your user at no extra cost. So this was, let's say, our preliminary work. And let me conclude by saying that this is, of course, one corner case of a wider issue. And the wider issue that in order to provide XR services, we need a very tight coordination and cooperation between local computing and edge offloading. To get that, we did not get into this in this paper, but to get that, you need to expand the range of offloading options that you have. For example, you need to use FR2 technologies like millimeter wave, sub-terahertz, and in order to make good decisions about that, you need an algorithm that we know how to do, but also, and crucially, you need knowledge. So you need to be able to understand the performance of, for example, FR2 technologies. You need to understand blockage. You need to understand, like we have done, the thermal behavior of the wearables. All of this needs to yield, is needed to have a good performance, which means that is needed, if you like, to make this whole XR and metaverse vision more likely to come true. And with this, I close. Thank you very much for your attention.